Gaitor, learning a unified representation across gaits for real-world quadruped locomotion. Our motivation is to investigate the challenges and opportunities of learning a unified representation across gaits for quadruped locomotion. The approach requires a variational autoencoder, which builds a structured latent space for locomotion. This takes the robot states as input, as well as the action, which is the desired base heading, desired gait, GK, and also a processed terrain image. These are encoded into latent space, concatenated together, and then decoded to predict the future robot states and the contact states of the feet, S+. This creates a latent space which is both disentangled and usefully structured. If we apply a trajectory within this space and decode it, we can solve for locomotion problems. To find a trajectory which can respond to terrain changes, we use a learnt planner. To train the learnt planner, we encode expert robot trajectories into latent space. We then plot these into a 2D manifold and extract the gait phase and the radius, as in essence in polar coordinates. We then use our learnt planner to predict the radius given the gait phase. Once we have trained the planner in latent space, we can predict a trajectory in that space. This is then decoded along with the action, the gait, and the terrain encoding to predict the future trajectory, which is sent to a whole body controller. This is the entire approach as seen during deployment. So we encode the robot states, take the action from the user, take the desired gait, use the planner to create a trajectory in the latent space, decode to predict the future trajectory, and send that to a whole body controller. We then repeat, and this is in a closed loop MPC framework. As we have mentioned, the latent space is usefully structured. In fact, this 2D manifold that we discover, if we have a trajectory along the horizontal axis, this increases the robot's swing height. If we have a trajectory along the vertical axis, this increases the robot's swing length. If we have an elliptical trajectory within this space, the robot takes meaningful steps. And if we adjust the eccentricity of this ellipse, we can then adjust the swing height and length independently. The VAE is able to infer correlations across multiple gaits. This means once a latent representation has been trained, it is possible to find continuous gait transitions from trot to crawl to pace. As a user changes the slider, the latent space structure physically changes, and this affects the contact schedule. We now show perceptive locomotion using our learnt latent space. The planner in the space creates the black trajectory you can see on the left. This responds to the terrain and adjusts the robot's gait characteristics. This helps the robot traverse the terrain. We show the same trajectory at half speed. Please watch the latent space trajectory and look at how it changes in response to terrain. The trajectory elongates along the horizontal axis in response to the terrain, and the robot has a much broader clearance. In fact, the robot has a 4.6 cm clearance above this 12.5 cm pallet. Now we show the continuous gait switching on the real robot. The robot begins walking in trot gait, and then transitions to crawl, before moving into a crawl pace hybrid. And then returns to crawl, and then back to trot. We show a few examples of perceptive locomotion using the learnt latent space. Thank you for watching.